Welcome to my talk. I'm Bian Zhenda from National University of Singapore, and I'm going to talk about using an online evolutionary approach to schedule deep learning jobs in GPU clusters. Recent breakthroughs in deep learning show the success of larger scale models and datasets. For example, the latest vision transformer pushes the state-of-the-art record of ImageNet top-one accuracy to 90%, while its model size is 30 times larger than ResNet, which is proposed in 2016. Similarly, the size of NLP models grows from 340 million parameters to billions of parameters in very few years. At the same time, there is also a significant increase in the size of datasets used to train these models. To deal with the increasing size of deep learning models and datasets, there has been a growing demand for GPU resources to speed up the computation of neural networks with distributed training on multiple GPU devices. For example, the Microsoft Philly cluster increased its scale by 5 times in just 1 year. But we know GPU resources are very expensive. So an urgent problem we are going to address in this paper is how to efficiently manage deep learning jobs in a GPU cluster to maximize the utilization. Let's start with how a GPU cluster works with deep learning jobs. Suppose we have a GPU cluster where each machine may have multiple GPU devices. As deep learning jobs do not have high CPU or memory usage, we just need to focus on the GPU resources. Then users continuously submit their jobs to the cluster in an online fashion, and each job requests for at least one GPU to start. A scheduler will be responsible for collecting cluster status and deciding an appropriate resource allocation accordingly. Like in this example, GPU1 and GPU4 are allocated to job 1, GPU5 and GPU6 are allocated to job 2, and so forth. The objective of the scheduler is to minimize average job completion time, which stands for the time between job submission and completion. To speed up deep learning jobs, a dominant practice is distributed data parallel training on multiple GPUs. This approach runs an identical model replica on each GPU and averages the parameters from all the devices after each step. However, the training performance is strongly related to the resource allocation. Especially, we need to find appropriate batch size and learning rate accordingly. As a result, deep learning jobs are hard to scale and hard to utilize idle resources. Let's look at some examples. There are two common ways to scale a job on different number of GPUs. First, we can set a fixed global batch size. However, when the number of GPUs is increasing, the local batch size on each GPU is decreasing, lowering the GPU utilization. Second, we can set a fixed local batch size on each GPU. Then the global batch size is growing, and the number of parameter updates per training epoch is decreasing. So the job needs more epochs to achieve equivalent accuracy. There have been some researches of resource scheduler for deep learning jobs. These schedulers tend to schedule jobs by using greedy strategies to determine the priority of each job to get resource. For example, Slack tries to maximize system-wide job quality by prioritizing jobs with predicted loss reduction. And Optimus uses shortest predicted remaining time first to minimize average job completion time, while Tertius uses least attained service first for the same purpose. However, these greedy strategies are inefficient to deal with online workloads because jobs in the cluster are dynamic and time varying. Also, the greedy strategies only take a limited number of solutions into account. Besides, these schedulers lack elasticity in their designs. Many of them are not able to adjust the number of GPUs or do not allow preemption. And no one so far is able to arbitrarily adjust the batch size for deep learning jobs, so that it's hard for the jobs to have the most appropriate batch size to achieve the best training efficiency. Our work is motivated by the idea that when we allow jobs to have elastic number of GPUs, we also need to support elastic batch size. More specifically, we allow the cluster scheduler to adjust the batch size according to the number of GPUs of a job. Also, to guarantee the training quality, we set a dynamic batch size limit for each job to avoid the generalization problem of too large batch size. For example, suppose we have a job with batch size of 24 and the limit is 96. On 2 or 4 GPUs, each GPU holds a batch size of 24, while on 6 GPUs, each one holds a batch size of 16. Based on the idea we proposed once, a scheduler for deep learning jobs that solves two problems of elastic batch size scheduling. The first is how to determine the batch size for each job. And the second is how to minimize the cost of running jobs with assigned batch sizes. Let me show our solutions to these problems one by one. First, how does the scheduler determine the batch size? We use an evolutionary search to continuously search for the solution. This algorithm is more suitable than greedy strategies because, first, it maintains a group of solutions that give a higher chance to reach high performance. Next, it is able to continuously optimize the solution for online workloads. Besides, scheduling decisions can be directly encoded into genomes, which is the basic form of solutions in evolutionary search. The evolutionary algorithm works with a population of candidate solutions in an iterative way. The population G starts with random solutions G0. Then at every iteration I, the new solutions Gi prime are generated by performing random operations on Gi. Gi prime will be evaluated, and the top solutions from it will be selected as Gi plus 1. According to the real-time status, the scheduler performs random operations to generate new solutions. The refresh operation removes inactive jobs out and adds new jobs in if necessary. And the crossover operation mixes up the existing solutions. And the mutation operation randomly replaces running jobs with waiting jobs. And the reorder operation packs the workers of each job for better placement. We then use SRTF to evaluate the candidate solutions. And we profile the remaining time based on the idea that recent jobs in a cluster may have similar performance. For example, it is model testing or hyperparameter tuning. Then we can build an online prediction model based on the recent job information to infer the remaining job time. We collect the real-time job information such as dataset, current loss, and process the workload size, and predict the training progress with uncertainty using a beta distribution instead of an exact number. Then we sample the training progress of each job from its distribution compute the overall remaining time of each candidate, and then select the top ones. We use random sampling instead of using exact numbers here because it can help evolutionary algorithm reach higher quality solutions. Next, we solve the problem of how to minimize the cost of running jobs with assigned batch sizes. The first cost is the convergence cost. Simply adjusting the batch size may affect convergence, which means the job needs more epochs to converge. To control convergence, we need to follow the linear scaling rule, which linearly scales the learning rate with the batch size. We also need to avoid a too large batch size gap before and after scaling, because this may result in a sudden increase in the training loss. Instead, we can increase the batch size gradually, as shown on the right. We also use a dynamic batch size limit R for each job to control the training quality according to its real-time job status. For example, to start a job, the batch size should fit in a single GPU. And to resume a job, the batch size limit will be halved if it's already rejected. And to scale up a job, the batch size limit will be doubled. And finally, when a job already runs for a long time, the batch size should be penalized. The next cost is scheduling cost. Existing schedulers handle online workloads with periodic offline rescheduling. That is, between a certain time interval, the scheduler pauses all the jobs in the cluster, reschedules the jobs, and then restarts them with new configurations. The rescheduling leads to two problems. First, the scheduler makes slow responses to job arrivals or completion. Second, there will be a large overhead because pause resuming deep learning jobs usually take more than tens of seconds. But at the same time, the GPUs are wasted. To reduce the cost, we designed the elastic batch size scaling, which can be automatically completed in the background and avoid stopping the training. There is a scaling agent deployed on each GPU. Initially, the scheduler starts a job and invokes the scaling agent, which loads the modules from the user script to the GPU devices and connects other workers of the same job. Then the user script is allowed to start the training. When the job needs scaling, the agent gets new configurations from the scheduler and pauses the training. Then it reconnects other workers and uses NCCL to synchronize its model through network. The migration can be completed at the end of any training step with very small overhead because we do not need to stop the training. And finally, the scaling agent resumes the user script to continue the training. Next, we evaluate our scheduler on a test bed with 64 GPUs on the TACC platform. Our evaluation trace includes 400 jobs from 50 different workloads as shown in the table. We compare our scheduler with some state-of-the-art deep learning schedulers, including the deep reinforcement learning scheduler, the optimal scheduler, and the Teresa scheduler. The differences of elasticity between these schedulers are shown in the table. We first evaluate the average job completion time. So from the results, our scheduler achieves the smallest average ACT. To further explain the improvement, we also evaluate the average execution time and queuing time, and our scheduler also outperforms the baselines. We also evaluate the scheduling scalability by scaling the cluster size from 16 GPUs to 64 GPUs. It seems that all the schedulers have similar behaviors, but we find that with more GPUs, for example, with 64 GPUs, our scheduler may have a larger improvement. Finally, to conclude, ONCE is a scheduler for deep learning jobs that achieves high elasticity, robust training quality, high training efficiency, and a small scheduling overhead.